Hello, welcome to the video, and in this video we will discuss about how to enhance the design of opamp or how to make the performance more better. So let's get started. And in previous video, we looked at some realization of op-amp and the output resistance of voltage controlled current source limits the DC gain, which consequently results in steady state error. And thus, in this video, we will look at more and more better performance. So we had an op-amp, and in our op-amp, we had our OTA, and ideally we only had a capacitor, and we had our current GMV which will go through the capacitor and integrate the current, and we had a buffer to isolate it from the resistive network, and we knew that GM by SC times V is our loop gain, but in in reality, buffers are not easy to implement in CMOS technology, and due to non-ideality, there exists the R naught, which is uh, uh, due to VCCS also comes with R naught or 1 by G naught, as it is not ideal current source, and it is a practical current source. So ideally, we were expecting the transfer function as gm by sc, but in reality we are getting the transfer function as gm by sc plus g naught, and sc plus g naught is basically a parallel combination of impedances, total impedances, and we can rewrite the equation in this format where we will be getting the dc gain and 1 plus s times the inverse of pole. So this also can be written as this form, where this is our non-ideality, and the higher the value of r naught, lower is the non-ideality, and that's why we want our r naught to be higher. So now let's say we use op-amp without buffer. So what will happen? So there is always a resistive load which is connected at the output, and there is like no matter how much r naught we increase, the gain is still limited due to resistive load network, and there are different possibilities to increase the dc gain, one of which is increasing the value of r naught, and modifying this is done by modifying the MOS transistor or the transconductor we are using, but this clearly does not help in the case of RL, so we have to use alternative topologies, and this is how we move towards the better performance of our op-amp. So the alternative topologies to increase the DC gain, let's discuss those. And initially we will assume that there is no RL and analyze the topology and then prove that it works well even with an external load resistor RL. So let's say we have our transconductor, and our transconductor has its non-ideal R naught, and we have our capacitor to integrate our voltage or the current basically. So the transconductance of our OTA is GM, and we want all of our GMVE current to flow through capacitor, but due to R naught, the non-ideality occurs and the gain is finite, which is limited. If we find a different way of converting this current to a voltage without having some of the current into some other component. So basically what we are saying that if we find a different way to convert this current to a voltage, and without going or without having some of that current going into some other resistive network, we can make a better integrator. And now let's analyze this situation. So what we have is basically nothing but we have a current source, we have R naught, and we have some resistive load which is Z, and instead of we are expecting that all our current should flow through Z and we should get I naught Z as voltage, but in reality the V out will be I naught times Z parallel R naught, and thus the gain is limited as we saw earlier. So to resolve this issue, we want our current not to go into R naught. And how can we do that? So instead of simply applying Z and taking the voltage across it, we make a current controlled voltage source. So this is how a current controlled voltage source looks like, where we have an op-amp, and in its feedback network, impedance Z is connected, and we have I naught at its input, where we have I naught as our input. So basically, we will be getting V naught is equals to I times Z, assuming that op-amp is in negative feedback. So how will it be happening? So initially, let's consider that this op-amp as ideal, meaning that this voltage is zero there. So this voltage is zero, and when we consider that this voltage is zero, all of the current is flowing through Z, and that's why we are getting V naught equals to I naught times Z. And when current source is non-ideal with coming with R naught, so again, at as this voltage is zero, both ends of R naught is at ground potential, and thus no current through R naught flows, and all the current flows through Z naught. And that's what we wanted earlier in our case, where we wanted no current from R naught, and we wanted all our current through an impedance Z. So of course, we will not have an ideal op-amp for current control voltage source. So we will have real op-amp, and which will be having omega u as unity gain frequency. And this current control voltage source behaves properly at a range of frequencies where the magnitude of loop gain is very, very, very high than 1. Basically, it is a range of frequencies within the unity loop gain frequency of this particular feedback loop. So this is how we can design where with non-reality, where our omega u basically must be higher than the frequency range of interest while designing an op-amp. So this is what simply means. So let's make our op-amp accordingly. So we have our transconductor, we have our current Gm times Ve, and this is what we implement as a current controlled voltage source with a transimpedance of 1 upon SC, as this capacitor is of value C. So at the output, we will be getting minus of the current times the impedance, basically GMVE times 1 upon SC. And this negative sign is due to inverting op-amp configuration. And to remove the negative sign, we can easily reverse the polarity of the OTA, meaning the current, instead of flowing outside, it will flow inside, and the sign is basically removed. This negative sign is basically removed, and we are getting whatever the expected gain we initially wanted. So while making an op-amp, instead of loading the transconductor with capacitor, we will follow the OTA using a current controlled voltage source. But to make a current controlled voltage source, we need some op-amp. So we will use the simplest form of op-amp we knew till now. So which is an OTA loaded by a capacitor. So we have our OTA loaded by our capacitor and our non-ideal resistor, and this is what we are applying to our main transconductor. So let's consider this circuit, and we have to look at the circuit and derive the transfer function. So let's ask few questions to ourselves. What is the order, or how many poles this circuit has? So basically, order is nothing but number of independent state variables in the circuit, or basically capacitive voltages or inductive currents. So here there is no inductor, so there are no inductive currents, but we do have capacitive voltages. And also, yeah, where this capacitor came from. So invariably, this capacitor comes between any node, and we know that invariably between any node and ground, there will always be a parasitic capacitance which we have to acknowledge and take in consideration. So here we have three capacitors, 1, 2, and 3, But we have C1 in parallel with C, and which gives us the C loop or this output node capacitance. So there are only two independent loops, and thus we have a second order transfer function with two poles. So the general guideline, or let's say a vague statement we can make, while considering that there might be a possibility of having zeros as well, and zeros can lie anywhere on the S plane. Doesn't matter if it's in the right hand part of the S plane. So wherever there is two parallel paths for output of first stage to the final output, i.e. there is output of first stage and this is output of final stage. So there are two parallel paths. One path is this one and one path is this one through the MOS transistor. So there is a path through GM2 and also there is a path through C. We can expect zeros in such a case. But this is not 100% sure. This is a layman vague term for the intuitive analysis. So what will be the DC gain when we find out the transfer function and set the value of S to be 0, we should get the DC gain. So for DC gain, all capacitors are open circuits. As we know, at DC, the capacitor acts as open circuit, and we can also find the DC gain independently without doing the full analysis in Laplace domain. Afterwards we can just do a sanity check, so that's how it will be useful. So let's consider circuit without by considering all the capacitors as open circuits. So we know at this point the voltage is basically the current GM1R1 times VE, and which is applied at this OTA, and which will give as its output voltage as the R0 times GM2, which is the current, and the input voltage or the gate voltage is basically GM1 times RO1 times VE. So the output voltage will be GM2 RO2 times GM1 RO1 times VE, and when this VE goes in the denominator, the DC gain comes out to be the multiplication of transconductances. So now we have this node and we have this node. So this is the node for, let's say, voltage V1, and at this node we have voltage V out over here. So we can make a matrix formation where we have impedances times the voltage or conductance time voltage, which is giving us the current. So basically at node 1 and at node 2. So since we are only interested in output variable, we will just simply use Cramer's rule, and this is, we know that this is the rule of basic circuit design. So this comes from there. So this we can derive by looking at the circuit, and we know that V naught is, using Cramer's rule, is nothing but the determinant of this matrix, just replacing this column by this column and divided by the determinant of impedance matrix. And by after solving this, we will be arriving at some equation, and that equation finally will look like this, and which is having a denominator of quadratic equation where the variables are s square, s, and a constant. So let's say a, b, and c. So let's do a sanity check for DC gain. Let's say s equals to 0, and we put s equals to 0 in the whole circuit. So we will get nothing but our transfer function to be gm1 gm2 divided by go1 go2, which is basically gm1 ro1 times gm2 ro2, and hence our sanity check is true and we are on a right path. So we have two poles and a 0, and the 0 is at gm1. So 0 is at numerator equating to 0, and we will get R0 at positive gm2 by c. So it is in right hand plane of s plane, right hand part of s plane. So it is very difficult to solve this denominator and find the roots by our conventional method. And in that case, we arrive at the point where we make approximation for the sake of finding the roots, provided that the two roots are very far from each other. So mod of s1 is very very less than mod of s2, where we have our roots at s1 and s2. And basically it simply says that if this is the equation, then and s1 and s2 are the roots of the equation, then this is true for the equation. Also, when we consider that this is the case, then for these two equations, we have two conditions where we say that in this equation, basically S1, mod of S1 is very, very less. So we can say that A times S1 square is negligible in this whole equation, and this equation cuts down to this part, which is approximately 0, and thus we get our s1 nearly about to minus c by v. And similarly, we can say that s2 is so large that this c part is much smaller than other two terms, and hence it can be neglected, and thus the equation breaks down to this part. So we get our s2 or our second pole at minus b by a. So let's keep in mind that the above approximation is only true when mod of s1 is very very less than mod of s2. So in our transfer function, this one, so this is our transfer function. Let's say this is a, this part is b, and this part is c. So we will get our P1, our first pole, at minus C by B, basically after putting the values, substituting the values. This is where we will get our P1. And let's, for our convention, for our easiness, let's say, let's multiply numerator and denominator by GO2. So this is what we will get where our P1 will lie. And we have done multiplying numerator and denominator by GO2 for the sake of making it look like there is some conductance in numerator divided by there is some capacitance in the denominator. Similarly, P2 will lie at minus B by A, and thus after substituting all the values from our equation and multiplying numerator denominator by C plus C1, we will get something like this, which is again some conductance divided by some capacitance. Now we have to review how one can tell the values of pole or the values of poles in a circuit intuitively, because we have to develop our intuitions as well. So we have a circuit, and in this circuit we can easily say that our transfer function is like this: gm1 upon go1 plus sc1, and which can be written like this. So we get our pole over here at minus go1 by c1. But in this circuit, let's take a circuit like this where we have the output through another amplifier, and this is like in this circuit, this circuit is very similar to the opamp we made, just the C over here is missing, which was like this. So by looking at this circuit, we can say that the transfer function of this part is gm1 divided by go1 plus sc1, and the transfer function is similarly for the second part. And we can say that P1 is lying at minus Go1 by C1, and P2 is lying at minus Go2 by CO2. But complications occur when we have a capacitive network. So now, in next video, we will discuss about Miller's theorem, and we will try to relate the case in which there is a C over here and there is no C over here, and we will relate those two cases and let's see how it makes sense. So this is all for this video. Thank you for watching.